Alright, so for my project, I am looking at congressional bills and trying to predict what happens to them. Do they become law? Do they die in committee? Do they get vetoed? And so on. So obviously there's a lot about politics and about Congress and about bills that isn't easily quantified. But there is also a lot that is. So I'm interested in the extent to which we can predict what's going to happen to a bill based on some of the easily quantifiable characteristics of the bill. So on the left, I have a diagram of the data that I used and where I got it from. And on the right, I have the Python script that I wrote to collect and process all of the data. And I have published that Python script in addition to my KNIME workflow, my R script, my R markdown file, and the HTML product of that markdown file on GitHub, so it's all available if you want to go look at it. So I combined data from 4 sources, really 3, an API for congressional data put out by ProPublica, bill texts from govtrack.us, and information about Congress member ideologies from a set of authors that I don't remember, but that is frequently used in political science research called DW Nominate, which is basically PCA of roll call votes and has 2 dimensions that I'll describe in a bit more detail later. So I first collected information from a bill endpoint from the ProPublica API and pulled information about how many co-sponsors the bill had when it was introduced, the subject area that it was working on, and so on. Next, I pulled the bill text from GovTrack, and I joined that onto the dataset. I also downloaded the DW Nominate file and then joined on the sponsors' scores on those 2 ideological dimensions using the sponsor ID, which was provided by the ProPublica API. I went back to the ProPublica API and went to a different endpoint to get more information about the sponsor themselves, like their date of birth, their gender, if they were in any sort of leadership role, and how many years they've served in Congress. And then I took a few more steps to recode that data. So I calculated how old the sponsor was when the bill was introduced using these 2 attributes, and I made an attribute that is the sponsor's congressional district, i.e. NC-04, although I don't think I actually ended up ever using it, but it's in there. I also performed text processing on the bill texts that I got from GovTrack, and I calculated a couple of attributes, just the simple length of the bill, how many English stop words it had in it, and how many numerics, series of numbers 480, for example. Those 3 attributes, length, stop words, and numerics, are all very highly correlated and collinear. So I mostly only just used length in all of my analyses. But I also calculated an attribute very specific to congressional bills, which is number of times the bill directly referenced existing U.S. code. And I did that using regular expressions. So basically I just looked for any time a string of this pattern, any of these patterns appeared in the bill. So chapter 240 of Title 9 U.S. Code, for example, and I just returned the length of the list of all of those references. And I also calculated simple average word length in the bill, which was fairly similar for all bills, as we'll see later on. And then finally, I did some last recoding, and this is pretty much to code my target variable, which is what ultimately happened to the bill. Did it become law? Did it die in committee, like that? Did it go to the Senate and then die? Did it pass? Did it do everything it had to, but it's not the type of thing that becomes law, so like a continuing resolution, which is how Congress keeps putting off not passing a budget. It doesn't change anything in the U.S. Code or make any sort of permanent change. It's just kind of an agreement by the government. Did it get vetoed? Which is only the case for 4 bills, but they're so qualitatively different from all of these others that I felt they should still be left out in their own category. And then other, which is really a grab bag. One of the bills is in SCOTUS litigation. Others, their most recent action is they had some random report filed on them. So it's only a couple dozen, and I just stuck them in this other category. So I ran this script and did all of this for 4 Congresses, the 112th to the 115th, which ran from 2011 to 2019. And those were all Republican majority houses, so they are fairly similar to each other. And the bills that I looked at are specifically bills that passed the House in any of those Congresses. So the majority, once I had all of the data, this took a long time to put together, but then the majority of my actual looking at the data was done in R, and I did all of that work inside of an R Markdown notebook, which I've published, and so that is what I will take you through. I think I need to refresh it because I updated something. And again, this has also been published on GitHub, so it should be available at that link if you want to go read it yourself. So I loaded all of the data from Python into R and took a look at it. I have all of the data there for you to look through. I've also provided a couple figures just to get a sense of the data. So one of the key attributes that I looked at is primary bill subject, which uses 32 classifications provided by the Congressional Research Service. And so that classifies bills as dealing with everything from animals to commerce to foreign commerce, foreign trade, to government operations and politics. And as you can see, certain categories were way more frequent than others. Bills dealing with armed forces and government operations, the budget, etc., government oversight were far more common in the 112th to 115th Congresses than bills dealing with social sciences and history or arts, culture, and religion. So this distribution needs to be kept in mind in further analytics down below because this is definitely skewed. And so whenever this variable is taken into account, it might impact the results. These are a few of the other attributes in the data set. Sponsor age. We can see most of the bill sponsors were in older ages. There is no second mode around the age of 30 like there is in the overall U.S. population. The U.S. population is bimodal at around 30 and 60 right now. But there is only the one mode here at 60, and that makes sense. Most members of Congress are older. The distribution of seniority also makes sense. Most people have served some, but not a long time, and there are some members who have stuck it out for the long haul. These two up top are the ideological dimensions that I referenced earlier. So the first dimension measures economic policy positions, so basically attitude towards government intervention in the economy. A lower score suggests that the person favors more government intervention, and a higher score predicts favoring more government intervention. And so when we take the fact that these were Republican-dominated Congresses into effect, as we can see here, it makes sense that there would be more sponsors on the right-hand side because there were more Republicans in Congress, more Republican sponsors, and therefore more sponsors who favored less economic intervention in the economy. The second dimension deals with relevant social issues of the day, is I think how the authors put it. And so today that's issues like LGBTQ rights. In the mid-19th century, that was slavery. And they've calculated these scores for everybody back to George Washington. So it's pretty cool data to look at. And these bill sponsors are actually fairly normally distributed on this dimension, while they are very polarized on this dimension, which is pretty interesting. Like I said, these were Republican-dominated Congresses, so most of the sponsors were Republicans. Kind of going along with that, most of the sponsors were also male. Most Congress members in the Republican Party are male, and so if most sponsors were Republican, they are also going to be mostly male. We can also see that more bills passed the House in each successive Congress. I'm not sure exactly what's causing that, but it should be taken into account in later analysis. And I also combined these two plots just to see if the proportion of bills sponsored changed in each of these Congresses, but it did not. So even though the number of bills is increasing, the proportion by party is staying the same. So it's not like Republicans or Democrats were increasing in quote-unquote productivity over time. They were both doing it at about equal rates. Finally, I look at those text processing attributes that I briefly mentioned earlier. These graphs are on log transformed X scales, which is appropriate for these four. It really shouldn't be for this one, but it was a whole lot easier just to use the same scale for all of them. And it doesn't irreparably harm this graph, so I just went with it. As we can see, most bill texts have about the same average word length. They're all written in English. But on all of these other attributes that kind of basically all have to do with bill length, most were not too long, just a couple hundred words long, but some were incredibly long, up to tens of thousands. That right-skewed distribution is the same for all of these attributes. I've also provided a correlation matrix of all the numeric attributes, so we can see again here that all of these attributes are pretty much collinear, representing about the same thing except for average word length, because that shouldn't change much no matter how long the text is, unless it's incredibly short. And we can also see that the polarized ideological dimension here is very strongly correlated with party, which makes sense. Having a lower score on this ideological dimension, i.e. favoring more government intervention in the economy, is associated with an increase in sponsor party, which we can see here from the coding of that variable means getting more democratic. So that all checks out. And while the rest of these relationships are not very strong, they do exist, and they're fairly strong. So it's not a complete sign to go no further. Finally, I looked a little bit at the target variable that I coded in Python. Certain categories of bill fates were more common. Becoming law and then dying in the Senate were definitely the most common. And like I said, vetoed, very much not common at all. I also simplified this, which is already simplified from hundreds of values to 6. I further simplified that down to a dichotomous variable for like the logit regression that I perform, where I said basically, did the bill make it through Congress? even if it eventually became vetoed? Or did it die somewhere in Congress, either in a committee or in the Senate? For some reason, it didn't make through. And here you can see the distribution of all of those results by subject area. Kind of interesting to look at. There's obviously something about bills that deal with Congress. That means they don't actually have anything to do with law. So a lot of continuing resolutions, House resolutions, setting rules of order, and things like that. Moving on to the analytics, I use 4 different methods to try and look at these results, which again is my purpose, trying to predict what happens to these bills. I did 1 unsupervised learning method, k-means clustering, which you can see here, and then 3 supervised learning methods, random forest modeling, naive Bayesian modeling, and logit regression. So for the k-mean and for the k-means and for the random forest and the naive Bayes, I performed all of those in KNIME, and I did try to do those in R and also in Weka, but I couldn't get any of them to work there. But I did get them to work in KNIME, so that was cool. I won't get too much into what I did here. It's basically just pre-processing whatever specific pre-processing needed to be done for that specific model, running the model, and then dumping the data straight back out so I could run back to R. And we can see that in R, I've explored the results of this first method, the k-means clustering, with a couple plots. I asked the k-means algorithm to produce 6 clusters. My thinking was there are 6 possible values in my result variable, and if I'm trying to get clusters that are like those results levels, I should ask for the same number. So this first one that I ran with pretty much every variable possible, I saw that pretty much the only thing, or the main thing, that's driving these clusters is bill length. Is so clear from this graph. And that wasn't very interesting to me. So then I went back to KNIME and I excluded all of those bill text attributes and I ran it again. And we can see the results of those here. And a number of attributes started being very informative, which were more interesting than just bill length. So here we can see I've plotted the bills colored by cluster on 3 dimensions, the 2 ideological dimensions and number of co-sponsors. And here you can see that 3 of the clusters are very clearly delineated by number of co-sponsors, and then 3 of them are really intermixed and were not separated by number of co-sponsors, and were not really separated by either of these ideological dimensions either. There's a split here between all of the bills on this DW-NOM1, which is the very polarized dimension, but it's not informative for any of the clusters. So then I went back up here and looked at what attributes might be informing the formation of these 3 clusters. And I looked, this table provides the mean of all the bills by cluster on each of these attributes. So these are the centroid coordinates for each cluster in 10-dimensional space, or 9-dimensional. And so I looked, these clusters are 0, 3, and 2. No, 0, 3, and 4. So I looked beyond these 3 attributes, what are the informative ones, and I've plotted those here. And so we can see that these first 3 were separated out by number of co-sponsors, And then these separate 3 were all very similar in terms of co-sponsors and these ideological variables, but were separated out by these 2 variables, sponsor age and sponsor seniority. One cluster is made up of bills sponsored by fairly young members in this region. And then the other 2 clusters, both were sponsored by older members, but some were older members who had been in Congress for less time, and some were sponsored by older members who had been in Congress for longer. So based on these 2 plots, I can see what the driving attributes are for these clusters. So my next question was, cool, I have 6 clusters. Do these clusters help me in terms of predicting the fate of these bills? And so to do that, I plotted the breakdown of bill fates within each cluster, and the answer is no. These are actually, the results are very well distributed within each cluster, and they do nothing to inform results. I was hoping, for, say, cluster 0 to be mostly went to Senate bills, and cluster 4 to be mostly became law bills, but that is not the case. So next I moved to supervised learning, which is definitely more appropriate for my goal. I just wanted to do the clustering because I think clustering is super cool, and it gave me the opportunity to do these 3D plots, which are also super cool. And I did 3 supervised learning models, which I listed earlier: random forest, decision trees, naive Bayesian modeling, and logistic regression. And I did the random forest and the naive Bayes back in NIME, and I did the logit regression in R. And for this random forest, I did one that was just a simple partition, and then I also repeated that with an X partition loop just to check the stability of that model, and it is stable. The average error in these bills is similar to the average error in these models is similar to the overall error in that model. And to make a long story short, the random forest model was about 75% accurate, which for machine learning is not great. We usually want at least above 80 and ideally above 90, so 75 is not great. But in defense of it, as I mentioned in the introduction, there is a lot going on in politics, and there is a lot that affects what happens to a bill in Congress. And the fact that given just these attributes, we can predict with 75% accuracy what is happening, I think is a victory. So I was fairly happy with it. I also looked at different more granular aspects of the model's performance, and for time, I'm going to skip over those. But I looked at accuracy within result to see if any fate was more accurately predicted than others, and I also looked to see if different subject areas were more accurately predicted than others, and for both of those, with a couple exceptions, the answer is no. They generally were predicted roughly equally. The next model type that I used was a naive Bayes predictor, which I again did in R, and it was not very good at all. Its test accuracy was 50.8%, so we were just barely better than randomly guessing. And for that reason, I barely explored it. I mostly just have it in here to show that nice. So this is actually worse. Somehow, I think I haven't set my seed. So every time it's using a random seed, and I guess this time was even worse. So yeah, this is bad for my purpose. So I moved straight on to logistic regression, and as I've said, I performed that in R. I ended up using my dichotomous outcome for this one instead of the full 6 level, because I tried to use multinomial. I tried to do multinomial logit in R, but I couldn't get it to work. So I just did the simple dichotomous logit, the regular GLM. And I did do logit. I used binomial distribution in a logit link, so it is logit, not probit or anything else. And based on that logit, I found that really 4 variables were statistically significant predictors of result with 95% confidence. And those variables were the Congress that the bill was in, its primary subject, the sponsor's age, and the sponsor's party. And I provided information here in terms of odds ratios because they're way easier to interpret than logit coefficients. So as we can see here, bills had lower odds of making it all the way through Congress as through each successive Congress. So more bills were passing and being sponsored, but fewer bills were getting all the way through. Secondly, certain subjects had greater odds of making it all the way through than the reference subject, which in this case was bills dealing with quote-unquote Congress, which was the most frequent category. So a lot of these subject areas, the odds of a bill passing in that area were far greater than the odds of a bill in the Congress subject area passing all the way through. Also, if a bill was sponsored by an older member, it had slightly greater odds of passing. For every 1 year increase in sponsor age, a bill's odds of making it all the way through Congress increased by 2.8 percentage points, which is not very great. It's not very practically significant. And finally, a bill's odds of making it all the way through Congress were strongly affected by the party of sponsorship as well. And I've also provided a couple of figures here going a bit deeper into performance, looking at the model's predictions versus reality over Congresses and by sponsor party, and those are available to look at as well. So in conclusion, the clustering was super cool to look at, but did not inform my purpose at all, and naive Bayes modeling was just terrible. So the random forest model or logit regression was definitely the best in terms of my goal, which again was trying to predict what happens to a bill if it passes the House. Does it keep going? I think if I had to choose one, I would prefer the logit regression, just because it allows for more tinkering, at least as far as I've found. You can only tinker with random forest model, but so much. The main limitation, as I've mentioned throughout all of this, is that there's a lot about politics that just can't be captured quantitatively. And I forgot to mention that you can see that from the odds ratio on the intercept in this logit regression, which is just absolutely massive. And that suggests there are a lot of things that are important in terms of predicting bill fate that I just haven't captured here. And so that definitely has to be acknowledged. There are certain things I think could be taken into account. So one idea I had was pulling a bunch of different opinion polling data over all these different years for a bunch of different relevant issues, and trying to make some sort of measure for public support for the bill, but that was simply too much to undertake for this. Additionally, going forward, I think it would be cool to pull information about the bills that have been introduced in the current Congress so far to use as a validation set. Of course, those would have to be bills that have made it all the way through. But we could also use a model built by logit regression to do actual complete predictions about all of these bills. And then a couple years down the road, compare that to what actually happened. The problem, though, is that all of the Congresses that I looked at had Republican majorities, and the House majority is now Democratic, so there would be some problems with generalizability of any of this to the current Congress. And additionally, while I was looking at only bills that had already at least passed the House, I could have taken an even wider look at all bills even just introduced into the House, which would definitely increase my sample size, but would also introduce a lot of problems with collecting all of the data. I would have a lot more missing data, but there might be a lot more variation just in all of these attributes with simply so many more bills to look at. So that was my project, and as I said, if you want to read this report that I made in R Markdown, or look at any of my other stuff, I've published it all on my GitHub, and it is available there for you to look at. Thanks.